So we're looking at now the gradient of a function which is not linear, and in the last exercise we looked at the chords and finding the limit of something as it approaches a point. We're going to use that same information here. So what we're going to do is find the gradient of the chord PQ. Now we don't have any values, all we know is that the graph is f of x, and we know therefore that here is x, that's our x value, and this one is x plus a little bit more, which is h. So therefore the coordinate is x and f of x, and the other one is x plus h and f of x plus h. So again, here's our x1, there's our y1, and there's our x2, and there's our y2. And so we know that to find the gradient, y2 minus y1 over x2 minus x1. So in this case it would be f of x plus h, which is our y2, take away our y1, which is f of x, all divided by, alright, x2, which is x plus h, minus our x1, which is x. And if I tidy that up, the only thing that's going to happen is the x's down the bottom will cancel out. So I'm left with f of x plus h minus f of x over h. And so therefore the gradient of the graph at point P. Now at point P, what are we doing to the h value? We are making it move towards 0, aren't we? So h is tending towards 0. So we let it equal to 0. And so basically this is the rule, therefore, for that. And this is what we call differentiating or finding the gradient by first principles. By first principles. So it is a long way about finding the gradient at a point, in this case at point P, and it can always be done that way. But this is an extremely important formula. So the limit as h tends to 0 of f of x plus h minus f of x over h. And look at the actual notation there, f dash x. F dash x is equal to the derivative or gradient. On this function, so let's go through a couple of examples here. We're told in the first one f of x is x squared plus x, and we're asked to find f dash x. Now we know by first principles that f dash x is equal to the limit as h tends to 0 of f of x plus h minus f of x all over h. Okay, we need to know some information here. We need to know what our f of x is equal to, and we need to know what f of x plus h is equal to. So coming over here and doing some working, we know f of x is equal to x squared plus x, because that was given to us in the question. So what is f of x plus h equal to? Well, wherever you've got an x, you're going to put x plus h. So x plus h all squared plus x plus h. And we need to expand that out and tidy it up. So the expansion for x plus h squared would be what? X squared plus 2xh plus h squared. And then we've got plus x plus h. Now that can't be tidied up. That is pretty much what f of x plus h is equal to. So let's come back over here and work out what f dash x is equal to by substituting in. So we've got the limit as h tends to 0. Now, what did we say f of x plus h was equal to? There it is, x squared plus 2xh plus h squared plus x plus h. And we're going to take away f of x. So take away, and f of x was x squared plus x. And what is that all over? Okay, that is all over h. We've got some tidying up to do here, obviously. So straight away I can see that x squared, and that's a minus x squared, so that cancels. And I've got plus x, and that would have become a minus x, so they cancel. Is there anything else that I can put together there? I don't think so. So I'm nearly there. I've got 2xh plus h squared plus h all over h. Now, can I take out a common factor here? Because I have to before I let h equal to 0. And I can. So again, I've got the limit as h tends to 0. Take out the common factor, and I've got 2x plus h plus 1. And that is all over h. And of course, the h's cancel out there. And so now's the only time we don't need to write that limit as h tends to 0, because we're going to let h equal to 0. And once we do that, we get 2x plus 1. And that is what my f dash of x is equal to. That is the derivative of the function x squared plus x. Or if you like, it is the gradient of that function. All right, what about the next one? Same thing, f of x is 2 minus x squared. Find f dash of x by first principles. So again, I'm going to write out my rule. So f dash of x is equal to the limit as h tends to 0. And it's very important that you put that bit in, the limit as h tends to 0. A lot of people tend to leave it out, and that makes the question incorrect if you do that. So that's all divided by h. That is my rule. So what do I need to find here? I need to know what f of x is. And I know f of x is equal to 2 minus x squared, because that's in the question. The other bit for that rule is to know is f of x plus h. And again, wherever I've got the x, I'm going to put x plus h. Oh, yes, so 2 minus x plus h all squared. And again, let's tidy that up. So it's 2 minus. Now expanding that gives me, and I'll keep the minus out there for a minute, x squared plus 2xh plus h squared. And so that's 2 minus x squared minus 2xh minus h squared. And again, I can't do very much more with that. I can now transfer that into my rule over here. So let's get going. So that's equal to the limit as h tends to 0. Now we know f of x plus h is 2 minus x squared minus 2xh minus h squared. And we know that f of x, because we have to take that away, is 2 minus x squared. And that is all over h. Of course, we've got to tidy that up. So let's see if there's anything there that cancels. Well, 2 cancels with minus 2. Minus, remember, minus here and a minus will make a plus. So minus x squared plus x squared. So we're still left with the limit as h tends to 0. And what's left up the top? Minus 2xh minus h squared. And down the bottom, we're left with h. And of course, we can take out a common factor there. So the limit as h tends to 0, take the h out, and you've got minus 2x minus h. And that is all over h. But of course, the h's cancel out. And so as we let h tend towards 0 now, so we're going to drop the limit part, our answer becomes minus 2x. So f dash of x, the gradient or the derivative of the function 2 minus x squared, is equal to negative 2x. And we did that using first principles. Hopefully, as we were differentiating using first principles, you were starting to see some patterns happening there. And the pattern that you should have seen was this one here. So what's actually happening is you drop the power down in front of the x, and then you decrease that power by 1 for each term in the function. And that's what f dash of x, or the derivative, is equal to. And that's the way we're going to do all our deriving, unless the question asks us to use first principles. So let's have a look at this example here in example 7. The question says, find the derivative of x to the power of 5 minus 4x cubed plus 1. All right, so what it's asking us to do is to differentiate it with respect to x. So there's a couple of different notations we could use here. But basically, because we've got no f of x or y there, we'd say that we are looking for d dx of x to the power of 5 minus 4x cubed plus 1. So we're differentiating that with respect to x. And so when we do that, using the quick method, drop the power down in front so it becomes 5, and decrease the power by 1, so 4, 5x to the power of 4. Drop the power down in front again, so it multiplies by the number in front, 3 times 4. In example 9, we're asked to find the gradient of the curve f of x equal to 3x cubed minus 6x squared plus 1. So that's the same curve as in example 8, but it is different in this case because we're doing it at the point when x is equal to 1, y is equal to negative 2. So we want the gradient at a point. Well, let's find the gradient of that curve first. So just the gradient of that function, we've already worked it out previously, f of x is equal to 3 times 3 is 9, drop the power by 1, so it's 2. 6 times 2 is 12, drop the power by 1, it's x, and the 1 disappears. So that's the gradient of the curve at any point on that curve. But what point do we want it at? We want it when x is equal to 1 and y is negative 2. But for this example, we don't need to use the negative 2. We're only interested in the x value. So we're looking for f dash of 1 at the point when x is equal to 1. So let's substitute that in. And again, in there. And you get 9 times 1 is 9 minus 12. So the gradient is equal to negative 3 at the point 1, negative 2. So f dash x is equal to negative 3 at the point 1, negative 2. In the past couple of examples, we've said that the derivative was f dash x. But if the equation is given as y equals, then we would actually say that it is dy dx. Means the same thing, it's just a different way of saying it, and it's just tying it in with the way that the question is presented. Also, in the other ones, the expressions were always in terms of y, or f of x in terms of x. Okay, now they don't always have to be in terms of x either. If they were in terms of, say, for example, t in this first one, then we're looking for dy dt. That means differentiate y with respect to t. So dy dt for this one, okay, we're treating it exactly the same way as the x. Drop the 2 down in front and decrease the power by 1, so it would become 2t. Have a look at this one. X is equal to t cubed plus t. So here we're differentiating x with respect to t, dx dt. dx dt is equal to, drop the 3 down, 3t, decrease the power by 1, plus, and then t becomes 1. The next one, z is equal to something in terms of x. So I'm looking for dz dx, and differentiating z with respect to x. 3 times 13 is 39. Decrease the power by 1 squared, plus, drop the 2 down, decrease the power by 1. So it's all the same thing, it's just getting the terminology correct. In example 11, same sort of stuff, but look, we've got some brackets there, and at this stage the best way to deal with this is to expand out your brackets. So let's start by doing that. And so you get y is equal to x squared plus 6x plus 9. All right, that's that bracket expanded out. And so now we want dy dx. We want to differentiate y with respect to x. And so we get 2x plus 6. Again, expanding the brackets is probably always going to be your best bet. What about the next one? There's a bit of work in terms of expanding this out. So again, you've got z is equal to, let's expand that bracket out, and you've got 4t squared minus 4t plus 1, and then times it all by t plus 2. Let's keep expanding that. So everything in one bracket needs to be expanded by everything in the other. So you get 4t cubed minus 4t squared plus t plus 8t squared minus 8t plus 2. Let's tidy that up. No cube, so it's 4t cubed minus 4t squared plus 8t squared plus 4t squared. T minus 8t is minus 7t, and don't forget about plus 2. And of course the question really wanted us to find dz dt, which would then give us 3 times 4 is 12. T, decrease the power by 2. 2 times 4 is 8. T to the power of 1 minus 7. So once it's fully expanded, not so difficult. Here you've got y equals x squared plus 3x. Well, this is an easy one since we've done all the others. So dy dx, differentiating y with respect to x, 2x plus 3. And this one, dy dx, is equal to 8x squared, and the minus 1 disappears, so it's just 8x squared. So there are many different ways of writing the derivative. We've already looked at f dash of x. We've looked at dy dx, if the function is in terms of x, of course, and d dx if we're not given a y or a f of x. So that is pretty much what this is on about here. That d of f of x dx is the same thing as f dash of x. So if we come down to this example, d of 2x cubed minus 4x squared dx is just basically saying, find if y was equal to 2x cubed minus 4x, find dy dx. So 2 times 3 is 6x squared minus 4. The next one, d dz, differentiating the function with respect to z. And again, 2 times 2 is 4z minus 3. And here is a d dz as well. So 2 times 2 is 4z minus 12z squared. So they're much of a muchness of what we've been doing. Have a look now at example 13. So the question says, find the coordinates of the points on the curves determined by each of the following. So we're actually looking for here the coordinates of the points on the curve where the gradient is equal to whatever it is given to us in the question. All right, so in this first one, we're told that the gradient is 9. But we also know one other thing about the gradient, and that is that dy dx, which is the gradient, is equal to 3x squared. Well, if that's the gradient and the gradient is 9, then those two things must equal each other. And so just solving that, x squared equals 3 and x is equal to plus or minus the square root of 3. Now remember, we're looking for a coordinate. A coordinate is an x value and a y value. So we've got the x values, substitute into the equation, which is y equal to x cubed. So let's take x equal to the cube root of 3 to start off with. So you get y is equal to the cube root of 3 all cubed. So another way you could write that is 3 to the power of 3 on 2. They mean the same thing. And the other one, when x is equal to minus root 3, all right, you get y is equal to minus root 3 all cubed. So again, they are our two solutions, but what are our coordinates? So here, when x is equal to root 3, y is equal to, I'm going to write it like this, root 3 cubed, beg your pardon. And this one over here, the coordinate is when x is equal to minus root 3, the y value is minus root 3 all cubed. So that's that one. Let's have a look then at B. And B is asking the same thing, but this time your gradient is equal to 0. So let's see what we can do at this one. We know the gradient of the graph, or the rule for the gradient of the graph, is 2x minus 4. We've just differentiated that. We're going to let that equal to 0. Letting that equal 0, you get 2x is equal to 4 and x is equal to 2. So this time we're only going to get one solution, and I'm going to substitute that into the rule, which was y equal to x squared minus 4x plus 2. So when x is equal to 2, you get y is equal to 2 squared minus 4 times 2 plus 2. And so that's 4 minus 8 plus 2. Minus 4 plus 2 is minus 2. Again, we haven't finished. We want the coordinate. And so the coordinate is when x is equal to 2, y is equal to minus 2. Okay, so the last one. In this one, we know that the gradient is equal to negative 6. So what else do we know about this equation? Again, we know the gradient of the rule. So dy dx is Now differentiate 4 and it disappears. Minus x cubed, drop the 3 down, so minus 3x squared. Remember, constants disappear. So that's what the gradient is equal to, or the rule for the gradient is equal to for 4 minus x cubed. And of course, we also know that we want the gradient at -6. We want the coordinate where the gradient is -6. So x squared is equal to -6 divided by -3 is 2. And so x is going to be equal to plus or minus the square root of 2. Again, I'm going to have 2 coordinates. So I'm going to substitute into the rule, which was y equal to 4 minus x cubed. And I am going to start with x equal to positive root 2. And so y would be equal to 4 minus the square root of 2 all cubed. Okay, they're not particularly nice values. You could get decimals if you wanted to, but I would probably leave it like that. So root 2 and 4 minus the square root of 2 cubed is your first coordinate. Your second coordinate happens when x is equal to minus root 2. So again, you get y is equal to 4 minus, now it's negative root 2 cubed. And we know that when you cube a negative, you end up with a negative. So really, y is equal to 4 plus root 2 cubed, if you like, because a negative and a negative is going to make a positive. And my other coordinate, therefore, is negative root 2. It's my x value, and my y value is 4 plus root 2 cubed. And so they are the 2 points on that graph where my gradient is equal to -6.